This is Loudoun County, Virginia, the data center capital of the world. It has more data centers per square mile than anywhere else on Earth. And right now, it is running out of electricity, not because of a storm or aging infrastructure, but because the power grid was never designed for this. Virginia regulators have warned that Northern Virginia may soon not have enough power for new data centers because the grid is running out of transmission capacity. Companies have already bought the land, billions of dollars are ready to be deployed, they have approved permits, but the utility company has one answer: wait. The AI revolution is not slowing down only because of chips. It is also running out of power, and that may become the biggest limit on the future of computing. To understand the crisis, let's start with a simple idea: power density. This toaster draws about 1000 watts to heat bread. Now look at the GPU, the kind used to train modern AI models. At full load, a single GPU like the H100 or B200 can draw 700 to 1000 watts. So in terms of energy, one of these chips consumes about as much power as a kitchen toaster. But here is where the real problem begins. You don't deploy just one GPU. Modern AI systems pack dozens of them into a single server rack. Systems like NVIDIA's NVL72 connect 72 GPUs together so they can act as one giant computer. A single rack like this can consume around 100 to 120 kilowatts of power. 10 years ago, a typical data center rack consumed around 5 to 10 kilowatts. In other words, the amount of power packed into a single rack has increased by more than an order of magnitude, and all of that power becomes heat. But the real issue is not just how much power these systems use, it's how concentrated that energy is. A toaster spreads heat across metal coils in open air. A GPU packs that same amount of energy into a tiny chip with almost no place for the heat to go. If that heat is not removed fast enough, the chips will shut down. Air cooling cannot keep up anymore. Moving that much heat with air would require enormous airflow, and the cooling system itself would start consuming a huge amount of energy. So the industry has shifted to a different solution: direct liquid cooling. Instead of blowing air across the chips, cold plates sit directly on top of the GPUs. Liquid flows through these plates, absorbing heat and carrying it away far more efficiently than air ever could. As a result, modern data centers are no longer cooled like gaming computers. They are cooled like industrial power plants. And that cooling system introduces another constraint: water. Most large data centers rely on cooling towers. Warm water carrying heat from the servers is sprayed through these towers and cooled by evaporation. The same basic process our body uses when sweat evaporates from our skin. But evaporation consumes a lot of water. In Northern Virginia alone, data centers consumed nearly 2 billion gallons of water in 2023. And that number is rising very fast. In other words, keeping these math toasters cool is starting to look less like computing and more like running an industrial facility. But solving cooling is only part of the problem. Because even if you can power the servers and cool the heat, you still need to connect the data center to the electrical grid. And that is where the real bottleneck begins. Connecting a modern data center to the grid is far more complicated than it sounds. Modern data centers don't consume electricity like normal buildings. A single large facility can require 100 megawatts of power or more, roughly the electricity demand of about 80,000 homes. Delivering that much power is not as simple as plugging into the nearest power line. To supply electricity at this scale, the grid relies on massive infrastructure: transmission lines, substations, and most importantly, transformers. You have probably seen small transformers mounted on utility poles outside houses. Data centers need the same thing, just on a completely different scale. The weight of large utility transformers can be hundreds of tons and stand several meters tall. And these machines are not mass produced. Each one is essentially custom built, designed for a specific location. As recently as 2021, utilities could typically receive a large transformer within about a year. Today, the timeline has shifted dramatically. Utilities are now reporting wait times of 2 to 4 years. Part of the reason comes down to a surprisingly obscure material, grain-oriented electrical steel used inside transformer cores. Global supply is limited and demand has skyrocketed due to renewable energy, electric vehicles, grid upgrades, and now data centers. The result is a bottleneck few people anticipated. So imagine you are a company planning a new AI facility. You can purchase the land, you can order thousands of GPUs, you can construct the buildings. But when you ask the utility company to connect the facility to the grid, the answer will be wait. Not for weeks or months, but years. In other words, the speed of the AI revolution is no longer determined only by semiconductor manufacturing. It is now constrained by power infrastructure. An industry that builds projects meant to last 40 or 50 years, not projects that is changing so fast. So instead of waiting for the grid to expand, there is another option. Build the data center next to the power source. This approach is often called behind-the-meter power. Instead of pulling electricity through miles of transmission lines, the data center connects directly to the generator itself. The power plant produces the electricity, the data center consumes it immediately. No long transmission routes, no overloaded substations. So the largest AI companies are beginning to bring their own power supply. And we are already starting to see this happen. In 2024, Microsoft signed a 20-year agreement to restart Unit 1 of the 3 Mile Island nuclear generating station. 3 Mile Island is best known for 1979 meltdown, but that was a different reactor. Unit 1 operated safely for decades, was shut down in 2019 for economic reasons, and now Microsoft is bringing it back. Around the same time, Amazon paid $650 million to acquire a data center campus located directly adjacent to the Susquehanna nuclear power plant in Pennsylvania. At first glance, these deals might look like climate initiatives, but the real motivation is more practical. They're solving a logistics problem. When you need hundreds of megawatts, the best solution is simple. Build the data center right next to the power plant. For many years, the limits of computing were defined by silicon. Chips got faster, models got smarter, and the assumption was simple. With enough resources, progress would continue. But that assumption is starting to break. The bottleneck is not an algorithm or a chip. It's a transformer that takes 4 years to arrive. It's a nuclear reactor being restarted because the grid cannot keep up. We have hit the copper ceiling. The AI race is quietly becoming an energy race. The companies that win won't just have the best models, they will be the ones that secured enough power. The most advanced technology humanity has ever built is now constrained not by math, but by metal, water, and wire.